Okay, so today's lesson is going to be over some more types of chemical reactions. So previously we've talked about how there's 5 main types of chemical reactions. We have synthesis, decomposition, combustion, single displacement, and double displacement. So you need to be familiar with those, and hopefully you learned those at your first level chemistry class. In AP chemistry, we're going to get a little bit more involved in some more complicated types of chemical reactions. One is called acid-base reaction. One is oxidation reduction, or just redox reaction. And one is called a precipitation reaction. We've actually already talked about precipitation reaction in another video in Unit 4. We're going to go over it a little bit more in depth. So let's start with acid-base reactions. In those, we are having an acid and a base react together, and we are using what's called the definition of Bronsted-Lowry. We are looking for the transfer of one or more protons, which is going to be represented by the hydrogen ion, between chemical species. We have to label things as acid-base and then conjugate acid and base. In an oxidation reduction, or that redox reaction, we're looking at how electrons transfer during a chemical reaction. We're going to learn how to assign oxidation numbers, and there's a set of rules we have to become familiar with to be able to decide if something went through oxidation or reduction. And then our last one is precipitation. And in a precipitation reaction, that is a type of double displacement reaction in which you have 2 aqueous solutions as your reactants. Remember, in a double displacement, they switch, and you will end up with 2 different products that are both compounds. One of those is going to be an insoluble solid, and then the other one is also going to be aqueous. For precipitation reactions, we have to know our SNAP ions. Remember, sodium, nitrate, ammonium, and potassium are always soluble in water. And AP simplifies those solubility rules down to just that SNAP. There are more complicated solubility rules, but AP always has one of those ions involved as one of the products. If it contains one of those ions, we automatically know it's soluble. And remember, when we talk about solubility, we would represent that as AQ, and the insoluble solid would just be S. Remember, aqueous for dissolved in water, and then S for becoming a solid. There's also another type of chemical reaction. AP really doesn't dig into this topic a lot, but I do need you to be familiar, and you should have seen this in your first year chemistry class, is something called a neutralization reaction. And in a neutralization reaction, it is another double displacement reaction. And in these, remember I showed you double displacement reactions, the outer 2 things will bond together and the inner 2 things bond together. Well, when H, which is a positive 1 charge, bonds with OH, which is a negative 1 charge, it gives you HOH. And you can leave it written like that. That is completely acceptable. Or, more often than not, it's going to be simplified down to just water, H2O. And then your other 2 ions are going to bond. So you have Na bonds with F. And so then, again, Na is a positive 1, F is a negative 1, so you just end up with NaF, and that is what we call a salt, which is an ionic compound. Now, these types of reactions are tricky because just because I add an acid to a base does not mean I only end up with water and a salt. It depends on the strength of the acid and the base. It also depends on if something is a limiting or excess reactant reaction. So I would never trust doing a neutralization reaction and just thinking you got salt water left over and you're able to drink it. That's a terrible plan, because typically one of these things was in excess. You're going to have some of it left over. And again, it depends on if it is weak or strong, if they're going to completely cancel out and form just water and just a salt. Usually there's other reactants that are left over at the end of the reaction. So let's talk about our acid-base reaction. So there are 3 different theories or definitions of how we define acids and bases. The first one is Arrhenius. Arrhenius acids and bases are going to be still used in AP chemistry. Arrhenius acids and bases is how we identify if something is an acid base based on if I put an acid in water, it produces hydrogen ions. If I put a base in water, it produces hydroxide ions. That's the Arrhenius acid-base theory. The second one is called Bronsted-Lowry acid-base theory. That is the one I'm about to teach you. The third one is called Lewis acid-base, And AP does not cover that, but you will cover it if you get into certain chemistry classes in college. So let's talk about the Bronsted-Lowry acid base. So Bronsted-Lowry acid is a proton donor. Now, when we're talking about proton donor, in chemistry, a proton is going to be just a hydrogen. When you talk about nuclear chemistry, a proton is often going to be written as just hydrogen. Same thing when we're talking about acid-base reactions. So when we're talking about a Bronsted-Lowry acid, it is going to donate or get rid of a hydrogen. The Bronsted-Lowry base is going to accept that hydrogen. Often in these chemical reactions, what happens is this hydrogen ion, because these are aqueous solution, is going to be added to water. And when we add that hydrogen to water, it is going to form something that is H3O plus. That is our hydronium ion. And that hydronium ion you're going to see often in these chemical reactions. In the problems, proton, hydrogen, and hydronium are often used interchangeably because they're all really representing the same thing. Because the proton is the hydrogen ion, and in an aqueous solution, the hydrogen automatically connects to that water to make the hydronium. So these two up here are going to be my reactants. So I'm going to have Bronsted-Lowry acid base. These two down here are going to be on my product side of the reaction. So the thing that accepts the hydrogen that the acid donated is the conjugate acid. The thing that is left over after the acid donates the hydrogen is called my conjugate base. Water is called amphoteric. That prefix amph is always going to be connected to you could live in or around or not in or around water. So like an amphibian, part of its life is in the water, part of its life is on land. That amph prefix is going to refer to water. And so an amphoteric species is something that can act as either an acid or a base. Water can act as an acid or a base. That's the most common amphoteric species we see. So down here on this problem, let's label these as we're just going to label it as acid base on our reactants. And then you have to say conjugate acid and conjugate base on the products. We have to memorize these definitions. And the best way to memorize things is just to do the problems over and over and over till it gets stuck in your head. So if I look at these things, I want to look at how it started, how it ended. That's how I decide which thing donated the hydrogen. So in this one, it starts as HF. It ends as just F. That means it donated a hydrogen. Well, based on the definition, the acid is the proton donor. So I'm just going to put an A under HF for acid. You can write out the word is fine too. In these reactions, one thing is always the acid, the other reactant is always the base. So my water is acting as a base in this reaction. It's that amphoteric species. HF started as HF. It donated its hydrogen and it became just F. If I look over here, the conjugate base is what's left over after the acid donates the hydrogen. So this is going to be conjugate base. And then it says the conjugate acid accepts the hydrogen when the acid is donated. So water started as H2O. It accepted that H plus ion and became the hydronium ion. So this is going to be my conjugate acid because it accepted the hydrogen from this side. We have to label those things. And then these are called acid-base pairs. So this is my acid, my conjugate base. This is my base, my conjugate acid. You always have acid base on the left, conjugate acid base on the right. There's something called oxidation numbers. This gets us into our redox reactions. An oxidation number is often the exact same thing as what we would expect an ion to have as a charge if it was bonded in an ionic compound. So like we'll just use table salt. So NaCl, Na is in group 1. That means it's a positive 1 charge. Cl is in group 17. That means it's a negative 1 charge. These are ion charges. And on the periodic table, depending on what group the element is in, many of the elements have a set ion charge. Often oxidation numbers match those set ion charges, but not always. So an oxidation number, by definition, or oxidation state, is what we say is a hypothetical charge that an atom would have if all the chemical bonds in the thing were completely ionic. But that's not true, because sometimes we have covalent compounds. Sometimes we have things that are mixed ionic and covalent, like if I had AgNO3, the Ag to the NO3, this is a positive one, that's a negative one, that is ionic, but the attractive forces in between the NO3 is actually covalent. So they get a little complicated. These oxidation numbers are going to be something we assign to the elements, and they are going to help us to keep up with that total number of electrons that an atom has gained or lost or shared in a reaction. It also helps chemists to be able to balance the equations and identify what's called a redox reaction. So we're going to learn some rules, then we're going to start doing some practice. These are the rules for oxidation numbers. Rule 1, elements have an oxidation number of 0. So if I have just zinc, it's 0. If I have O2, which is a diatomic element, but it is considered an element, it is 0. If I have carbon 60 in its pure form, which is a solid, it is still 0. So if it is just that element's, no matter what the subscript is, if it is just an element, then its oxidation number is 0. Hydrogen is always going to be a positive 1, but there are a couple exceptions in which if you have a hydride, which would be the second element, it's a negative 1. AP really doesn't do exceptions for oxidation numbers. So hydrogen would be a positive 1. We just memorize it's always a positive 1. Oxygen is always a positive or negative 2. Again, there's something called peroxide. And if we saw a peroxide ion, it would actually be a negative 1. Again, AP sticks with the most common rule, not the exceptions. So oxygen will be a negative 2. If you have something that is a monatomic ion, so it's an ion that's just by itself, mono means one, atomic atom. If it's just an element by itself, it takes on the charge of whatever it would if it were just from the periodic table. So sodium is in group 1, positive 1, oxygen's in group 16, negative 2. Iron is a transition metal. It can take on different charges. It tells us it's a positive 3, so its oxidation number is a positive 3. And silver, even though it is a transition metal, you should have memorized silver and zinc are always positive 1, and zinc is always positive 2. It would take on that charge. In a compound, the overall charge has to be neutral. When you guys learned how to write chemical formulas, you learned that we have to make our positive and negatives cancel and make an overall net charge of 0. That's what we're doing. But if it's a polyatomic ion, we want to make the overall charge equal to whatever the charge is of the ion. So in this one, oxygen had to be a negative 2 because the rule says oxygen is a negative 2. Negative 2 times 4 gives me negative 8. Sulfur has no rules. If it doesn't have a rule, you just have to follow through and do process of elimination to figure out what it is. So if I want an overall negative 2 for this, if this is a total of negative 8, then this has to be a positive 6, because positive 6 plus negative 8 gives me a negative 2. And we're going to practice this in a minute. If there are no elements present in the compound, then you just assign the more electronegative element its normal ion charge. So chlorine is more electronegative, because remember our trend for electronegativity is increase up, increase across, with your noble gases being the most, your halogens being the most electronegative elements. And so chlorine is closest to fluorine. Fluorine is the most electronegative element. And so you will assign its normal charge, which is negative 1. And then because it is a compound, we have to cancel the charge. It has to be negatives and positives equal, so sodium will become a positive 1. If there are 2 elements in the compound that doesn't have a rule listed, then you always will know one of the negative ions, and then you just assign the metal ion its normal charge. So in this one, oxygen is a negative 2. Negative 2 times 3 gives me negative 6. This is a compound, so I want it overall to equal to 0 again. So that's a negative 6. Since there's no rule for sodium and no rule for nitrogen, then I'm going to assign my sodium its normal charge, which is positive 1. So then I have positive 1, negative 6. I need it to be overall 0 a net charge of 0. So that means my nitrogen is going to be a positive 5. Positive 1, positive 5 gives me positive 6, and that cancels my negative 6. In these problems, we have to label our oxidation numbers, and then we figure out which thing goes through what we call oxidation and which thing goes through reduction. The way that I memorized it is with oil rig is the acronym. We have a lot of acronyms in AP we memorize to help remember really complicated things. This is one of them. So there's always a transfer of electrons in these oxidation reduction reactions. Something is losing electrons, something is gaining electrons. The way I remember it is oil rig. So oil is going to be oxidation involves loss. And specifically, we're talking about electrons. Rig is going to be reduction involves gain. Again, we're talking about electrons. So step 1 for these oxidation reduction problems is label the oxidation numbers. Step 2 is figure out which thing went through oxidation and which thing went through reduction. So let's start by assigning this problem oxidation numbers. I'm going to flip back to our chart to make sure that we understand it. So this is in its ion form. If I go back to my previous slide, it says for ions, oxidation numbers for monatomic ions equal their charge. So if I look here, this is a positive 2, so that is its oxidation number. I typically still write a positive 2 up here because it just helps my brain. The next thing I have is just pure sodium. If I go back here, oxidation numbers that are just an element by itself is always 0. Remember, zinc by itself is just 0. So this is going to be 0. When you're doing oxidation numbers, don't worry about the coefficients. They are to balance the number of atoms. For right now, we are just looking at the element. Over here, I have copper. Again, that is an element by itself, so its oxidation number is 0. And then this sodium is in its ion form. Remember, in chemistry, if it's just a plus, it means +1. And so its charge is a +1. Once I know these oxidation numbers, then I can use my oil rig to figure out what's going on. I recommend my students, when they first start out doing this, to write it out like this to help them see what's going on. So I would say Cu starts as a positive 2, and it goes to a 0. And then Na starts out as a 0, and then it goes to a positive 1. Okay? Then we got to think about electrons. Electrons are negative. They are a negative charged ion or subatomic particle. So we have to figure out from this to this, how would it become 0? Well, if I have a positive 2, to get to 0, I had to gain a negative 2. So I had to gain 2 electrons in order to go from a positive 2 to a 0. I had to gain 2 electrons. So if it gains, reduction involves gain of electrons. So since this, let me erase my 2. So since this gained 2 electrons, copper went through the process of reduction because reduction involves gain. Over here, oxygen went to a positive 1. That means it had to lose 1 electron because it went from 0 to positive 1. So in a neutral atom, it would have an equal number of protons and electrons. If you lose an electron, then you now have more protons in your nucleus than you have electrons. And so whenever I lost that 1 electron, it went to a positive charge. Oxidation involves loss of electrons. So since I lost 1 electron, then this is going to go through the process of oxidation. We are going to practice this topic much more in section 4.9. We will talk more about oxidation and reduction. Then the last type of reaction is that precipitation reaction. For a precipitation reaction, it is going to always produce an insoluble solid. We only have to remember the SNAP rules to decide which thing as a product will not be soluble. It would be aqueous, meaning that we only care about that insoluble solid. So let's do some practice problems where we're applying all this. I know it's a lot of information, but let's do some practice problems where we apply this. So in these problems, it says, which of the above reactions can be classified as acid base reaction, a redox reaction, or a precipitation reaction? As we're doing these problems, we're also going to go through and label things as their oxidation numbers and also label as acid base, conjugate acid, and conjugate base because we need practice with those. So in my opinion, of these three, the easiest one to see is precipitation because in a precipitation reaction, one of your products is going to be a solid. So this letter C is going to be my precipitation reaction because I have aqueous calcium, aqueous sulfate ion. They come together to make a solid calcium sulfate. You are only seeing the net ionic equation. There would have been other spectator ions that we don't care about. In this reaction, it only shows us which thing became a precipitate. So we've marked that one out. We've done it. So then acid-base reactions, often you can identify those. Most acids start with a hydrogen as their beginning element. Not all of them do, but most acids, many acids do. And then also you now have seen that hydronium ion. And so in this problem, the second one has hydronium. This thing starts with hydrogen. So this is going to be an acid-base reaction. Okay, so let's go ahead and label these as acid-base and conjugate acid and base. So I'm going to have to flip back to our slide. So an acid is the thing that donates a hydrogen. The base is something that accepts the hydrogen. So then your conjugate acid is the thing that accepts it on the product side. Your conjugate base is the thing that's left over. So let's start with these, the acid and base. So in this problem, on my reactant side, the only thing that even has hydrogen is this. So this is my acid. That means that this automatically has to be my base. Then, going back to my notes again, the conjugate acid accepts the hydrogen that the acid donated. So on the other side, the conjugate acid is going to accept that hydrogen. The conjugate base is going to be what's left over. So the thing that accepted the hydrogen, because this gave up its hydrogen, the thing that accepted it was this thing. So this is my conjugate acid. The thing that's left over after that acid donates its hydrogen is H2O because it goes from H3O positive, gets rid of the H plus, becomes H2O. So this is going to be my conjugate base. In this one, this is just the anion. This is just a polyatomic ion that has a negative charge. When it accepts that hydrogen, it becomes HC2H3O2 because this had a negative one charge, and that hydrogen that this one got rid of has a positive one charge, so it just becomes HC2H3O2. Okay, so by process of elimination, this is my redox reaction. So now let's go through and identify and put on our charges for each of these things. Now, when you do redox reactions, it is going to be sometimes a little tricky because you're assigning these charges, but they're not always going to be in the order that you expect them to be. So in this one, we have carbon and hydrogen. So hydrogen had a rule. Again, I'm going to go back to my slide. It says hydrogen is always a positive one. So we're going to make this hydrogen be a positive one. But there are 6 of them, so 6 times positive 1 is positive 6. Carbon, therefore, has to cancel the charge of positive 6 by being a negative 6. Remember, ignore the coefficients for right now. They don't matter for the charges. If there are 6 carbons and overall they are a negative 6, then carbon is going to be a negative 1. This one is oxygen by itself. If it is in its elemental form, whether it has a subscript and is diatomic or not, it is going to be a charge of 0. Over here, oxygen is always a negative 2. That's one of my rules. Oxygen is always a negative 2. If it is a negative 2 and there's 2 of them, it's a total of negative 4. That means that overall my carbon has to cancel with positive 4. Well, there's only one carbon this time, so it is just going to be a positive 4. And then here, oxygen is a negative 2 because it's always a negative 2. Hydrogen has to always be a positive 1. So then we want to look and see what things changed and what things didn't change to figure out which one went through oxidation and which one went through reduction. So hydrogen didn't change because it was a positive 1 here. It was a positive 1 there. This one had carbon as a negative 1, but a positive 4 over here, so it did change. And then this one had oxygen as 0, and then it changed to a negative 2 in both places on the other side. So it did change. So the only thing that didn't change is the hydrogen. So we don't care about it because it didn't go through oxidation or reduction, just stayed the same. So then we got to look at these and figure out what happened. So remember, I recommend for right now, writing out carbon starts as a negative 1 and it goes to a positive 4. And then oxygen is just O, not O with a mark through it. That's my 0. So oxygen goes from a 0 to a negative 2. Okay, so now let's look and see what happened here and how these things occurred. So remember, electrons are negative. So in this one, for it to go from a 0 to a negative 2, that means it had to gain 2 electrons. Over here, we went from a negative 1 to a positive 4. This one's tricky. We know that it had to lose, but it lost a lot of electrons. It lost 1 electron here, and then it kept losing 4 more. So it actually lost 5 electrons. So then we have to go back to oil rig. Oil oxidation involves loss of electrons. So this one lost, so this one went through oxidation. Reduction rig, reduction involves gain. This gained 2 electrons, so this one went through reduction. Let's try one more. It gets easier the more you practice these. So we got to figure out again acid, base, redox, and precipitation. So let's start with precipitation. Precipitation is going to be my second equation because it ends up with a solid on my product side. So this is my precipitation reaction. Then I got to figure out my acid base. Acid base is always going to have some sort of involvement of hydrogen in it. So if I look here, letter C looks like an acid base reaction because on this side I have hydrogen. It ends up giving it away, and I end up with chlorine on this other side. So this one is going to be my acid-base reaction. Let's label our acid base and conjugate acid and base. So acid is the thing that donates hydrogen from my reactant side. So this has to be my acid, which means this has to be my base. Now for conjugate acid and conjugate base, let's look back at our rules. It says that the conjugate acid accepts the hydrogen. It's the product that has accepted the hydrogen, and my conjugate base is the product that is left over from donating the hydrogen. So when this gives up its hydrogen, what's left over is Cl. That is going to be my conjugate base. The thing that accepted the hydrogen over here, it went from NH3, it gained a hydrogen plus and became NH4 plus. That is going to be my conjugate acid. That means that this last example up here is my redox reaction. Let's go through and label all of our ion charges. Bromine, Br2, it's in its diatomic form. If it's an element by itself, it is going to be 0. OH, this one is a polyatomic ion. We haven't ran into that yet. It's the first time we're going to run into it. In the other example I had on the previous page, these were elements, so I made them equal to that net charge of 0. So overall, I wanted them to be 0. But this one is not. This one is a polyatomic ion. And so my rule is hydrogen is always a positive 1, and oxygen is always a negative 2. Well, if that's true, the negative 2 plus 1 gives me a negative 1, which is what I want for the charge. This is an ion by itself, so it is a negative 1 charge. This is a polyatomic ion. It has an overall charge of negative 1. So oxygen has to be a negative 2 because that's what my rule says. So it means it has a negative 6 Well, bromine needs to cancel, but not all, because it's a polyatomic ion. I want it to overall end up being a -1. So then I'm going to end up with bromine needs to cancel part of the charges, but not all. So it's going to end up canceling with the +5, because +5 minus 6 gives me a -1. So bromine is a +5. And then down here, oxygen has to be a -2, hydrogen has to be a +1. So again, we want to look and see what has changed and what hasn't changed. So if I look here, bromine went from a 0 to a +5, so it did change. Oxygen went from a -2 to a -2 to a -2, so oxygen did not change. But then hydrogen went from a +1 to a +1, so hydrogen also changed, or did not change, so it doesn't matter. So in this one, bromine was both oxidized and reduced. It went from 0 to -1 and from 0 to -5. That happens occasionally. So for this first one, I'm going to say that bromine went from a 0 to a -1. And then bromine went from a 0 to, this time it went to, I said negative a minute ago, I meant to say +5, I think. So then I got to think about what happened. Okay, so for it to go from a 0 to a -1, that means it had to gain 1 negative electron. For it to go to 0 to +5, that means it had to lose, it lost 5 negative electrons. So oil oxidation involves loss. So this one went through oxidation. Rig, reduction, involves gain. So this one went through reduction. So we marked our acid base and we got our redox reaction. So your next two sections are going to be digging more into that Bronsted-Lowry acid base. And then the last section of Unit 4 is going to be over digging into these redox reactions a little bit deeper. So if you still are a little unsure about these, it gets easier with practice. You just have to get those rules stuck in your head and the definitions for Bronsted-Lowry acid base stuck in your head in order for this to be able to become easier.